Hey, everybody in Academic Algebra 1, what is up? This is Mr. Schaub, back for your Week 2 video lesson. If you'll recall, Week 1, we got down the rest of our exponent rules, and so now hopefully we're feeling pretty good on how to work with exponents, how to work with powers, use all 7 of those rules to simplify expressions. Of course, you always know that I teach you that for a reason. The reason we need to know how to work with exponents is because we're moving into a new type of function in this lesson. They're called exponential functions. So the first thing we're going to look at, the essential question for this lesson is, what are some of the characteristics of the graph of an exponential function? So we're going to define this. We're going to take some notes on it first, but since this is an exploration, we always like to start by just trying some things out and see what happens. So the first thing we need to understand is an exponential function is an equation where the variable, the independent variable x, is in the exponent of a power. Okay, we've never seen anything like that before. We're used to dealing with linear functions where x is on the main line. It always has an exponent of 1. Okay, so technically it is a base with an exponent of 1. But now we're going to be looking at equations in this form. If you look over here, y equals 3 to the x. So you can see our variable is actually in the exponent, and that has a unique effect on what happens to the y value, the outputs. All right, so let's take a look at the first exploration here, exploring an exponential function. All right, so it says, complete each table for the exponential function y equals 16 times 2 to the x power. In each table, what do you notice about the values of x, and what do you notice about the values of y? All right, so we go ahead and zoom in on this one a little bit here. All right, the first thing we're going to do, so we have our function here. And so to evaluate a function, remember, nothing really changes. We're going to take the values that they give us for x, which are, if I can use my laser pointer right here. All right, these are the values they give us for our independent variable x. And they want you to put a 0 in, a 1, a 2, 3, 4, 5. All right, so remember, when we evaluate, all we do is take those values for x and we plug them in here where x is in the expression, and then we got to simplify to figure out what the y value is, okay? Once we do that, then we're going to have an x value and a y value. It's going to be an ordered pair, something that we can graph on the coordinate plane to see kind of what these functions look like in graph form. All right, so first off, this is how we evaluate it. It's a little bit different, but if you understand how to work with exponents, it's really not that bad. So you can see we're going to take, let me get my lightsaber out. We're going to take 0, since x is equal to 0, we're going to put a 0 in for x in the function. And since that's in the exponent, what we really have is 16 times 2 to the 0 power. All right, now I want to direct your attention over here. We do have to still follow our order of operations. So if we take it all the way back to when we learned about PEMDAS, all right, please excuse my dear Aunt Sally, exponents come before multiplication. So what that means is a lot of students are going to be tempted to multiply 16 times 2 first and then raise it to the 0 power. But that is not what we do. Order of operations says we do the exponent first. So 2 to the 0 power is 1. Anything to the 0 power is 1. Hopefully you remember that. And then after we simplify the exponents, then we simplify multiplication. So we multiply last. 16 times 1 gives us 16. All right, not too bad there. So let's do the rest of them the same way. And you can see I kind of shorten up my work here after a second. But so if we put in a 1 for x, now we have 2 to the first power, which is 2. And then we multiply that by 16. So you can see that multiplication by 16 is always going to be our last step. Okay. If x is 2, what do we get? Let's take a look. All right. So now, and I did it all in one step here. I expect you to be using your calculator just to make sure that you're doing these right. If you put it in the calculator exactly like this, 16 parentheses 2, and then after the parentheses, you can raise it to the second power, you will get the same answer. All right, so we get 64 here. That's because 2 squared is 4. 4 times 16 is 64. All right, moving right down the line, I'll just show you the rest of them here. Okay, so we've got when x is 3, we raise 2 to the third power. That gives us an 8. 8 times 16 is 128. When x is 4, 2 to the 4th power is 16. Remember, that's not 2 times 2. It's 2 times 2 times 2 times 2. 4 2's being multiplied together. All right, so that's where we get 16. 16 times the 16 out front is 256. And then when we do x equals 5, 2 to the 5th power is 32. 32 times 16 is 512. So these are the values that we get when we evaluate that function at these 6x values. All right, so 16, 32, 64, 128, 256, 512. Do you see any patterns there? Okay, there is a pattern. We're doing the same thing to the number every time to get the next number, but it's not what we're used to. With linear functions, when x goes up by the same amount, y always went up or down by the same amount. You could add or subtract the same amount from the y value each time, and you could see patterns that way. Well, exponential functions are a little bit different. So let's take a look. To get from 16 to 32, we can multiply that by 2, right? We're doubling it, okay? That should make sense because we're raising, every time in this table, every row, we're raising the exponent by 1. So that we're adding another factor of 2 that we're multiplying onto that number. That's essentially what we're doing. So to get from 32 to 64, we can multiply 32 times 2 to get 64. 64 times 2 is 128. 128 times 2 is 256, and then to finish the pattern out here, 256 times 2 is 512. So let's take a look at the second example, and we'll see if we can catch any patterns here. Okay, so now notice the only difference here is that 0, okay, so the x values, they're not going up by 1s anymore. Now it's increasing by 2 each time. So let's see what happens. It's the same function as the last table, all right, so 16 times 2 to the x, but we'll see what happens to the values as we increase x by 2 every time instead of increasing by 1. So first thing, we already did these 3 in the last table. So, you know, when we evaluate it at 0, 2, and 4, those values are in our last table. So we really don't have to do that math again. You're more than welcome to if you want, but you don't need to. Okay, so what if x is 6? Then we're raising 2 to the 6th power. We're going to get 1024. And you can see these numbers get big really, really fast because we're increasing the exponent. And the exponent tells us how many of those bases to multiply together. So every time we're multiplying it by more and more numbers. So that's why they grow so fast. All right. And then next, if x is 8, our grand total comes up to 4,096. And if x is 10, we're raising 2 to the 10th power and then multiplying that by 16. So I believe that's 2 to the 10th power is 1,024, and then we multiply that by 16, and we get that huge number. Okay, so what are we doing to get from the first value to the second one, and then from the second value to the third one, and so on and so forth? Have you figured it out yet? This time, the numbers we have to multiply by 4, all right? And that's because I doubled the gap between our x values, and when you do that, you can also double the number that you multiplied to get your next value. So with exponential functions, it's a different type of pattern, but the patterns are still there, and we can kind of see them forming. But these patterns use multiplication and division rather than addition and subtraction, which is what we're used to. All right, so I backed it out a little bit here, so we can go back and revisit the question that they ask us here. What do you notice about the values of x, and what do you notice about the values of y? So I think the best way to answer this, I've got my answer over here. Let me clear it off for you. All right, what I think you really need to notice about this is when x goes up by 1, the y values double each time. When x goes up by 2, the y values get 4 times bigger each time. So that's the pattern that we should be seeing here. Hopefully you see that just like I do. There definitely is a connection between the x values and the y values. All right, so we can see those patterns forming here. All right, so now let's hop down to exploration number 2. Now we're going to do the same process, but you can see that we have a new function. All right, we're not using 16 times 2 to the x anymore. It's 16 times 1/2 to the x. So I would really recommend you use your calculator, all right? If you plug it in, like I said, you know how to do this by now. If you plug in 16 parentheses, 1 divided by 2, close parentheses, and then raise that to whatever power you have here for your x values, the calculator will give you the right answer. Just make sure you're using those parentheses appropriately. All right, so I'm going to move a little bit faster through this one because we've already done this process one time. I just want to kind of show you what answers you should be getting when you're doing these problems. All right, so for example, when x is 0, we're going to raise 1/2 to the 0 power. That's just going to be 1. Everything raised to the 0 power is 1, so we get the same answer for x equals 0. Okay, and that should not surprise anybody. All right, next though, look what starts happening. Because we've changed that number 2 to a 1/2, when we multiply a whole number like 16 by a fraction, we actually get a smaller result. So it's the same as dividing by 2. Multiplying by 1/2 and dividing by 2 are really the same thing. So this is really 16 times 1/2 means you're finding 1/2 of 16. So that answer is going to be 8 there. All right, and then let's go ahead and clear the rest of these out, and you can see what the rest of our answer is going to be. If that pattern continues, we evaluate all of these, and all we change is that x value, that exponent, then look what happens to our y values. We start at 16, then 8, then 4, then 2, then 1, then 1/2. Anybody see a pattern there? Hopefully you do. Let's take a look. All of these numbers, to get to the next number, you have to divide by 2. All right, and remember what I said, multiplying by 1/2 and dividing by 2 are the same thing. So that should make a lot of sense to us. The higher that exponent is, the more 1/2s we are multiplying 16 by. All right, so for example, when x is 4, we're taking 16 and we're multiplying by 1/2 times 1/2 times 1/2 times 1/2. 4 1/2s all multiply together, then we multiply that by 16. So that's giving us a much smaller number. And that pattern will continue going. So you can kind of assume, if x is 6, then y is going to be 1/4, and then 1/8, and then 1/16, and it'll just kind of keep going that way. You're going to keep dividing those numbers by 2. All right, so here's what I want you to do. For this last table, I want you to pause the video, and I want you to try and fill that table out all by yourself, and then after you do that, you can play the video again. You'll see what I got, and you can see if it matches up. All right, so take your time, pause the video, because your teacher's going to bust out a freestyle flow. Take your time, make sure you do the work. Your teacher's going to help you because he's not a jerk. Go ahead and fill in the numbers in the table if you are willing and if you are able. One more thing, y'all, before I'm through. Hope you got the same answers that I do. Okay, I hope y'all enjoyed that. That was, yeah, you know what? I'm so bored that's where I'm at right now. This is how I keep myself entertained. All right, take a look at the answers you should have, and hopefully you can see the pattern here. Just like in the previous two tables, we multiplied the first numbers by 2 to get the next number, and then when you go by 2s with the x's, you had to multiply by 4. Well, you can also see that every time in this table, if you got the answers I did, that we are dividing by 4 to get our next number. Okay, remember, dividing by 4, multiplying by 1/4 means the same thing. So that's how exponential functions work. We've got one more question down here, so let's zip down to the bottom and talk about this one. Zoom in a little bit. Okay, do you think the statement below is true for any exponential function? And the statement is this: as the independent variable x changes by a constant amount, all right, so same amount every time, the dependent variable y is multiplied by a constant factor. Okay, that is in fact true. Let's take a look here. You should be able to see this, okay? What I said, and hopefully you are thinking the same thing, you kind of understand where I'm coming from here. It is true. As long as x goes up by the same amount every time, the y values will be multiplied or divided by the same factor every time. Because remember, multiplying and dividing really are the same operation. Like I said, if you're dividing a number by 2, you could also multiply that number by 1/2. So you can multiply by the reciprocal when you divide, just like we learned with fractions. So yes, that is true. Every time, as long as the independent variable x is going up or down by a constant amount, then the y value will be multiplied by a constant factor. All right, so now we're jumping down to the second page. Yes, we got 2 pages of notes today, but I also have a pretty fun activity for your application for part 3 that I think you're going to enjoy. So it all evens out. All right, so let's take a look at this. I do want you to graph these on your own to kind of take a look at the pictures I have. What it says here in exploration number 3, it wants us to sketch the graphs of the functions given in explorations 1 and 2. How are the graphs similar and how are they different? So I'll answer that over here in this big green blob in a second. But what I did was I copied the points from the first table here, the points from the first table in the second exploration here. All right, so we got the blue exploration, we got the green exploration. So first, these are the numbers we got. I'm going to zoom in on that a little bit. All right, so you can really see what's going on here. All right, so this is our function down here at the bottom, y equals 16 times 2 to the x power. So if we take the numbers we got, so remember, we were plugging in 0 through 5 for x, and these are the numbers that we got for y when we plugged it into the function. If we graph those, and now you have to make sure you get your scale right. Now, my scale's not perfect, but it's good enough to see what the graph looks like, okay? Now, I couldn't really fit 512 on there, but I wanted to space them out evenly. I didn't feel like going 100, 200, 300, 400, 500 and just stopping up here. So I decided to skip, to go by 50s instead. All right, so we can at least graph the first 5 points on here, and that gives us a good picture of what the graph's going to look like. And you can see what happened here. Now, I'm just trying to get these as close as I can. Is it going to be perfect? Of course not. Am I going to get 16 exactly on the y-axis here? No, but we can get close. So that's all we have to try and do. All right, so when x is 1, y is 32. So you see we're not quite to the 50 line, but we're closer. And then when x is 2, y is 64. When x is 3, y is 128. All right, so you can see all those are those points are pretty much where they're supposed to be. 256, that's going to be right above the 250 line. And we don't get a straight line. A linear graph or a linear function has a graph that's a straight line. An exponential function is always going to have a graph that's a curve. All right, so let's see what it looks like when instead of having that 2 as our base in the power, we have a 1/2. That's the second exploration we looked at. So these numbers here are all the numbers. I took them directly from the table in exploration number 2. All right, so we start on the y-axis. The biggest value we have is 16. So it's kind of nice. We have 8 lines here. We can go by 2s, and we can fit 16 on there. So that's where we're going to start, 0, 16. And then this function is decreasing. The previous function was increasing as x got bigger. This one is decreasing as x gets bigger because we're raising a fraction to a power. So here's 0, 16, and then 1, 8, and then 2, 4, and then 3, 2, 4, 1, 5, and 1/2. And then beyond that, this is where it's going to go. So we're never going to get to 0. Remember, this number is always going to be divided in half, but it's never going to get to 0, right? It's always going to be like, okay, after this would be 1/4, and then 1/8, and then 1/16, and then 1/32, but it's never quite going to get to 0. So that's why we have what's called an asymptote here, and you're not really going to need to know what that means, but hey, it's a fun word to say anyway. So asymptote is what when your graph approaches a value but never quite gets there. So now let's compare. All right, so the question asks us, how are the graphs similar? How are they different? Okay, so I know it's a lot of writing, but this is, remember, these are my notes. This is how I teach you about this stuff. So hang in there with me. All right, what I said was both graphs are curved instead of straight lines like a linear function. All right, so that's how they're similar. You can see one is curved up and one's curved down. So that's what I said in the next line. The first function has a base of 2, which makes the function get bigger, which is called growth. And the second function has a base of 1/2, which makes the function get smaller, and that's called decay. We'll talk a little bit more about those terms later. But that's basically the difference between these two functions. You see, everything is the same, except the base of the power here is 2, and the base of the power here is 1/2. And that's really the big difference. That's why this blue function grows as x gets bigger, and the green function decays as x gets bigger. All right, so that brings us to the note or the definitions section of our video today. And we really just have one major definition here, and it's right here. Y equals ab to the x. This is the general form of an exponential function, and we're going to talk a little bit about what this means, what these a and b values are here. So first thing you need to know is there are some conditions that need to be met for it to be an exponential function. All right, one of those is a cannot be equal to 0. All right. If a is 0, so picture this. If a is 0, then we know that if this is a 0, 0 times whatever b to the x is, doesn't matter because 0 times anything is 0. So if a is 0, then the whole function is just y equals 0. And that's just a linear function. That's a horizontal line. All right. So to be exponential, a cannot be 0. Also, b cannot be 1. All right. So if you think about that, let's go back to our overly sized exponential function here. If b is 1, then we have 1 to the x power. And what is 1 to any power? 1 to the first power, 1 to the third power, 1 to the 10th power. They're all 1. Because remember, you're multiplying 1 times 1 times 1 times 1, however many times we have up here. So this will always be 1. And therefore, if this value is always 1, no matter what x is, then when we multiply that by a, we're just going to get a constant again. So the reasoning here behind b not being able to 1 raised to any power is 1, so x doesn't really matter. That's going to be a linear function again. And finally, b has to be greater than 0. B cannot be a negative number, and it can't be 0 either, because obviously 0 to any power is equal to 0. All right, and also, if b is negative, then we won't have a function. You just can't do it. You just got to make sure your b value here is always a positive number, but that's not 1, okay? All right, and then right below that, a little bit of information about the graphs of exponential functions. So if we look over here on the left side, when the b value, and remember I was talking about this before, when the b value is greater than 1, the function grows. So it's either going to grow, let me get my laser pointer out, it's either going to grow up this way, okay, or it'll start out negative and it'll become a bigger negative value, okay? And so I know this doesn't seem like it's growing, it seems like it's decreasing, but it really means the function, the absolute value of the function is getting larger as x gets larger, okay? Over on the other side, on the right side here, if the only other option for b to be, since it can't be negative and it can't be 0 and it can't be 1, the only other option is that b is between 0 and 1, and that's what our proper fractions, that's what we call those, okay? And when that happens, the function decays. So decays means, just like in the real world, the word decay means to waste away or to break down. Okay, same thing's happening here. We start with a large value, and then it continues as x gets larger. The function gets smaller and smaller. Okay, even if we have negative values, we get closer and closer to 0. So the absolute value of the function gets smaller when b is between 0 and 1. Okay, and these are really important. We are going to talk about them more in the next couple units. We're going to take, or not units, sections. The next section is over just exponential growth, and then the following section after that will be over exponential decay. But we need to know these terms right here, so I want you to write these down as well. The a value in the function right here, that is called the initial or starting value. Okay, both terms mean the same thing, so they're both acceptable. And then the b value, the base, just the base, remember, not the exponent, is called the growth factor. All right, so initial value for a, growth factor for b. Okay, so you got all the information you need. Let's do one more example together on the notes just to make sure we know what to do in this section. So let's start with my laser pointer here. Okay, let's read the directions. Use the exponential function given below, right here, to fill in the table and sketch a graph of the function. Okay, so remember, to sketch a graph, all you need are points that you can put in the coordinate plane. We get those points by filling out a table. Okay, so a couple things to remember. First off, let's show you this part first. Okay, our function is f of x equals 24 times 3/4 to the x. Okay, so remember, we had two different options that could happen when we're looking at an exponential function. Either that b value, that growth factor, is between 0 and 1, where you have a decay situation, or it's greater than 1 and you'll have a exponential growth situation. So this case, our b value is 3/4. So you can see that right here. And since that's between 0 and 1, the function should get smaller. It should decay. So let's take a look at the table. Okay, now, we call x our independent variable for a reason. We can pick any numbers that we want for x, but it's best to use some simple values for x, like start at 0 and just start going up by whole numbers, because those are easy to work with. We can do this pretty easily. I still expect you to use your calculator, but this is how we're doing it. Remember, we take the 0 for x, we plug it in for x in the function. All right, so that's what I've got right here. All right, I plugged 0 in for x, and then we just work this out. And yes, I expect you to use a calculator, but you can also understand how it works, by hand, because we understand these rules now. So anything to the 0 power is 1. So when we evaluate this function at x equals 0, then f of 0, remember, f of x is just a fancy replacement for the y variable. So this means the same thing as a y variable. All right, so f of 0 is equal to 24. So we're going to put a 24 in here. All right, and then 1, likewise, when we evaluate 1, we do exactly the same thing. We just replace that x value with a 1 instead of a 0. And when we work it out, okay, 3 to the 4th, or 3/4 to the first power is 3/4. 3/4 times 24 is 18, so our next value is 18. Okay, next point, you can see here, these all are just evaluated the same way. When we do f of 2, we put a 2 in for x. We square 3/4, we get 9 over 16, because remember, the power of a quotient rule tells us that we can square the top and square the bottom independently. So when we multiply the fraction 9/16 times 24, we get 13.5. All right, the rest of your values, you should get 10.1 when you put a 3 in for x. And again, I rounded this off. All right, so we're not looking for perfection. We're just trying to get some points that we can graph on the coordinate plane. All right, so we get 3 and 10.1, 4 and 7.6, 5 and 5.7. All right, shoot me an email if you don't understand where those numbers came from. I just did them the exact same way I did these first 3. I just didn't feel like showing my work for every problem. So, sue me. Sorry. But anyway, hopefully you understand that. Now all we have to do is sketch the graph. So what we're going to do is just plot each ordered pair the best we can. We want to make sure we fit all these numbers on our graph. So let's take a look at how I did it. All right, you can see the biggest value we have to fit on our graph on the y-axis is 24. Since I have 8 lines to work with, I'm going to go every line is worth 3. All right, and that'll get me right up to 24. So, and at the bottom, I can just go by ones because we only have to fit in 0 through 5 along the x-axis. All right, so when I plot these points where they belong, the point 0, 24 is right here, 1, 18, and then 2 and 13.5, 3 and 10.1. Again, I'm just trying to get it as close as I can. It should form a smooth curve like this if you do it right. Maybe yours won't be perfect, but like I said, that's not really what we're looking for. We're just trying to get them in the right area. All right, so here's 4 and 7.6, and then 5 and 5.7 right there. And we can connect those with a smooth curve because that's what an exponential function graph is always going to look like. All right, party people, that's it. That's the rest of the notes. As far as, in the interest of keeping this video short, I know I already failed at that, but I'm not going to go through the practice problems. I think you can figure them out on your own. Don't forget, we have a Zoom lesson, a Zoom class on Thursday at 10 a.m. where I'll probably go through a lot of these practice problems that I didn't do on the note-taking guide. But remember, if you open up Mr. Schaub's notes, that file in there, it's got 3 of the 9 practice problems you need to do worked out, so you can see how to do one. Of course, you were responsible for getting the rest of them done. And then your application this week, I made a brand new Kahoot challenge. It is not timed. All right, there's a bunch of information on this page. There's some new types of problems. We got access to the premium features of Kahoot, so I've been playing around with those. It's been a lot of fun. So basically, you are going to be graded on the application for this section. Here are the rules, all right? You have to do a Kahoot challenge. You're going to be competing against the other people in your class, and we'll see who gets the best score on the Kahoot challenge. So there are some, like I said, new types of questions. There's some true-false questions. There's some open-ended answers. There's a puzzle question or two, and there's some multiple choice. And I even threw a poll in at the end just so you can see all the cool new features of these Kahoots. All right, so You can't do it on this because it's a video. But there is a big link at the bottom. If you open up your performance packet, there's a link there. It should take you right to the Kahoot challenge, and you can do it from there. And I believe, you need to let me know if I'm wrong, but I believe you can even start this Kahoot challenge and then stop and then pick up and finish it later. All right, so it is not timed like it usually is. So you want to take your time, make sure you're getting the right answers on those. That's going to do it for me. Read the notes. Come to my Zoom session. Come to my office hours on Friday. Remember, anytime 10 to 3 on Friday for your B-Day teachers. You can email me questions, and I'll be right there ready to answer them. So get those last-minute questions in before you submit this packet. All right, we had 100% completion the first week. Really super excited about it. I hope we do it again. All right, so if I don't see you've submitted your packet by Friday, I'm going to send you an email, make sure everything's going along okay. All right. Remember, I'm here to help, so ask me questions anytime. I'll get to them as soon as I can. Thanks for listening. Hope you enjoyed it. Try not to make fun of me too much. I'm out.